Okay, today's lesson is on an introduction to sequences in series and their recursive rules. Today is just going to be, like the title states, just a basic introduction. What is a sequence? What is a series? And what are recursive rules when we look at those? So, today's particular lesson is fairly long. Because the way iStep did, we had to sort of combine a couple things into one. So hopefully you've already watched some of this at a different time, and hopefully it won't be so long. But the first thing we're going to talk about is what is called a sequence. Now, you may have seen this as something, maybe something else, but a sequence is all it is really is just a list of numbers. It's an ordered list of numbers or terms. Okay. So for example, like term 1, and then term 2, and then term 3, and so on. That would be a sequence. It's just a series of numbers listed with commas and everything like that. There are two types of sequences. There are infinite sequences and finite sequences. You could probably figure out what's what. But an infinite sequence is a sequence with no end. It's a sequence with no end, and how you see this is, you'll see the dot, dot, dot. So you'll see 1, 3, 5, 7, and then dot, dot, dot. That designates that it's going to go on forever, and that's an infinite sequence. Whereas a finite sequence is a sequence with an end. So you'd have 1, 3, 5, 7. You might see some dot, 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 but then it gives you a final term. In this case, 13. So that would be a finite sequence. We're going to focus our attention on finite sequences and just looking at sequences that do have ends. So a sequence is it's a sequence of numbers, and they're not random numbers. They're numbers that have or show a pattern. So if you look up here, you could see a pattern in these numbers. You're adding 2 every single time. So that would be a sequence. So a sequence can be specified by an equation. So let's look how we can find the terms of a sequence given its rule. So down here you have this would be an equation of a sequence. So this is where you'll see a sub n. So what this is the answer of however many terms is equal to 4n plus 5. So what the n represents is the term number. So term 1, you would plug 1 in. Term 2, you would plug 2 in. Term 3, you would plug 3 in, and so on. And then the a sub n is the actual term. So term number, like term 1, term 2. So like this is term 1, this is term 2, term 3, term 4, and then the term is the actual value. So you'll see what I mean here. So what we're going to do is we're going to create a table where you have the term number n, and then a sub n is going to be the actual value. So term number 1 means that you would just plug 1 in. So 1 in for n, 4 times 1 is 4, plus 5 is 9. So the answer of that term number would be 9. Think of A as an answer. Term 2. It says to go to the first 5 terms, so we'll do that. 4, 5, 2. If we put 2 in, that's 2 times 4, which is 8, plus 5 is 13. 3 times 4 is 12, plus 5 is 17. You should see the pattern here. Clearly it's adding by 4, so you could just assume that it's going to continue to add by 4. to get the rest of the numbers. And so that's writing out a sequence. So the answer actually would be all of these in a list. So 9, 13, 17, 21, and 25. And that would be the answer to that, the first 5 terms of that sequence. Sometimes the sequences look kind of crazy, so there's a little bit of work to do here. But same thing, we're going to draw our table of n and then a sub n, which is the actual value, the answer. By plugging in 1, a little tricky here, 1 minus 1 is 0. So I have 1/2 to the 0 power. And if you know your power properties, anything to the 0 power is 1. So 1/2 to the 0 power is 1 times -3 is -3. 2, we'll keep going, 4, 5. 2 minus 1 is 1. So 1/2 to the first power is 1/2 times -3 is -1.5. 3 minus 1 is 2. 1/2 squared is, and you could do this in your calculator, 1/2 squared or 0.5 squared is 0.25 times 3, and I have to get the calculator here. So 0.25 times 3 is 0.75, negative 0.75. And you can see the pattern happening here. It's being cut in half. So the next one's going to be negative 0.375, and the next one will be negative 0.1875. So it's just being cut in half. So that's a sequence. A sequence is just a list of numbers in an order of some sort that follows some sort of equation or rule, we call them. So here, again, is a sequence, and so we can just plug in the term numbers 1, 2, 3, 4, 5 and get all of our list of terms that are in that particular sequence. Same thing here. These would be all the terms listed within the sequence. So my sequence for B would be -3, -1.5, -0.75, -0.375, and -0.1875, and that would be the answer to that. Okay, again, sequence, list of numbers, follows a rule, and this is how you would find the terms within a sequence. That's essentially what we're doing here. A series is not a list of numbers. It is an expression that indicates the sum. Big key word there. Sum. Box it, bold it, whatever you want to do, highlight it. It's an expression that indicates the sum of the terms in a sequence. Sorry, mistake there. Sum of, this is all messed up. Sum of terms of a sequence. It's supposed to be the. There we go. It's a typo here. Sequence. It uses sigma, which is this fancy E, to express a series. I'm going off the page there. So a series, let me zoom out here. There we go. A series is an expression. So if the sequence is the list of numbers, so like here would be the sequence, the list of numbers, a series would be all of those added up. So it's the sum of the sequence, of the particular sequence. So, and just like before, so an infinite series, okay, is we don't really get into infinite in both of them, but infinite series just because they deal more with pre-calc. You'll get into infinite series. They call that limits in pre-calculus and in calculus. But infinite series would be a sum that approaches infinite. See, it's a sum that approaches infinity. That means that the sum is, if you kept adding up all the numbers would just get infinitely large. Whereas a finite series, this is where we'll actually talk about this. A finite series is where a sum approaches, I can't spell, approaches a particular number. Sometimes when we add up all of the numbers within a sequence, it gets to just one single number, and we'll talk about that a little bit later. But that's that. So this is what a sum will look like down here. So summation notation is one way to express a series. We express it in this sort of sigma here. We can use summation notation to write either finite or infinite series, though we're going to focus on finite series. We also can refer to summation notation and sigma notation. So this is this. You'll see there are different ways to write this. You'll see it in sigma or you'll see it S sometimes. But basically you have the formula or the rule right here that you're going to use. The n is going to be where it says n equals 1. That is going to be the first input for this particular rule. So you'll plug in 1 first. That's what this means. This is your first term. And then the top number is the last term. So what this means is I'm going to plug in 1, because it's the first one, then plug in 2, plug in 3, plug in 4, plug in 5, plug in 6, and that's it. I go from 1 to 6, plugging it in, and the sum would be the addition of all of those numbers. Okay. All right, move on to the next page. Here's some examples of what sums look like. So zoom in here a little bit. So the first one is the sum of 2k from 1 to 6. So what we do is we just plug, since 1 is our first number, I'm going to plug in 1. 2 times 1 is 2. Okay. Now I'm going to plug in 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. And I ran out of room. 6 times 2 is 12. The summation notation says that we are going to now add all of these terms. 2 plus 4 plus 6 plus 8 plus 10 plus 12. You add them up, let's see, 6 is 12, 20, 30, 42 should be your answer. 42 would be the sum of that series. Okay? So this right here, you just plug it in right there. Same thing here. We're going to plug this in. Now we do have to keep in mind that there's a half on the outside, so whatever answer we do get, we have to cut in half. So if I'm going from 1 to 4, if I plug in 1, it's just 1. So, k is there, so it's just 1, but then it's half, so it's 0.5. Okay. So you can do this two ways. You can cut them in half each time, or you could just do all the sums and then cut it in half at the end. It's not going to make any difference. 2 cut in half is 1. 3 cut in half is 1.5. 4 cut in half is 2. We add all these up, and you get, see, half and half is 1, 2, 3, 4, 5. And you just add it all up. Now this works really well when we have small amount of numbers that we need to add. Imagine if we had the last value said like 1,000 on the top. What if it was like 1 through 1,000 and I had to make 1,000 numbers and add up all 1,000 numbers? Well, good news is there are formulas for this. So you don't actually have to do 1,000 things and add them all up. The process of evaluating a series would be very tedious if it were 1,000. So below are formulas that we can use to find the sums of 3 special types of series. Okay. The first rule is that if you have a number in front like this, you can actually move the C to the other side. So this would then equal C times the summation of A of K. Okay, so you can just move this to the outside and multiply it later, as opposed to multiplying each individual number every single time. Just do all the sums and then multiply it by the end. The other property that we can use is if we have multiple terms in a sum, we can actually split them up. So instead of adding one to the other and doing the sum every single time, you can actually split this up and do the sum. Oops, didn't do that right. Jeez. A of K plus the summation of B of K. So you can actually split them up. And this is going to be some important properties when we're actually calculating these sums. Okay. If you have multiple terms, you can split them. If you have a number in front, you can move it to the outside. So here are 3 specific types of sums. One is where it's just a constant. It's just a number. Like it would be the sum of 5 or something like that. This one, so it's constant series. This is a linear series to where this is an actual variable in which you'd have to substitute in. And then we have quadratic. So let me show you what this looks like. The formula for a constant series is to simply just take whatever n is and multiply it times c. So this would equal just n times c. Now none of these things you're going to have to remember. You'll be given all of these formulas on tests and quizzes, so you just need to know how to use them. If you have just a constant, you'll just do n times c and that'll be the answer. So when you have the sum of 10 going from 1 to 3, essentially the first term is 10. Because it's just 10 and there's no variable, that means that the first term will just be 10. The second term will just be 10. And the third term will just be 10. If you add them all up, it's 30. But that's why this formula works. So you just multiply your n times your c. 3 times 10 is 30. Here, when you have a variable, this is a linear series. The formula for doing a linear series, a little bit more complicated, it is n times n plus 1 over 2. So a little more complicated here. So what we're going to do, so how do we do this? So if you have a variable, this is what you're going to use. Now this is an example of a linear summation here, where I have something plus something. What we are trying to teach you to recognize is that you have a linear portion of this and you have a constant portion of this. We can apply the property up here that states that if I have two terms inside here, I can split them up. So what we're going to do is split this in half. So really, this is just the sum 7 n equals 1 of 2n minus the sum of 7 n equals 1 of negative 12. By splitting it up, it allows us to do both of these separate rules. I can do the linear one and the constant one. So let's start with the linear one. The linear one states that it is n. Remember, n is the number that's on top. So 7, parentheses, 7 plus 1 over 2. And then that 2, that it's in front, remember on the out, we can just, basically it's like this. The entire thing is just multiplied by 2. Okay, so what I have here is 7 plus 1 is 8 times 7 is 56. Now, the 2 here could cancel if you wanted to do that. But 56 divided by 2 is 28 times 2 is 56. So I end up with 56 here minus, now the constant, remember, you just take n times c. It's just, n times c, which is 7 times negative 12. So don't need the minus sign there. I split that up wrong. So the minus sign is already there, so it's just 7 times 12, which is 84. The minus sign was, I shouldn't have pulled the minus sign over here. The minus sign, so this is actually positive 12. The minus sign's right there. So I have 56 minus 84, which is negative 28. The sum of that one would be negative 28. Okay. Last one is a quadratic. So with quadratics, the formula is even more complicated. So you have n times n plus 1 times 2n plus 1 all over 6. Again, these are formulas that will be given to you. And so what you are essentially going to have to do now with the quadratic is split it into its 3 parts. Split, split. Okay? So what I have, the first term will be 4 times the quadratic. So I have 4 times this whole thing up here. N is the number that's on top. So 5 times 5 plus 1 times 2 times 5 plus 1. It's going to get smashed in here. All over 6. Then I have minus 2 times the constant one, which is 5 times 5 plus 1 over 2. And then the constant one, which is just whatever n times c is. So 5 times 7 is 35. So plus 35. So I have all that I need to do. So first off here, 2 times 5 is 10 plus 1 is 11. So I have 11 there. So I have 4 times 5. 5 plus 1 is 6 times 11 all over 6 minus 2 times 5 plus 1 is 6 times 5 is 30 over 2 plus 35. So now let's clean this up. 5 times 6 times 11 divided by 6 is 55. So 4 times 55 minus 30 over 2 is 15 times 2 is 30. And then plus 35. 4 times 55, I need a calculator for this. 4 times 55 is 220. So now I have 220 minus 30 plus 35 is 225. Oop, 225. Now, you might be thinking to yourself, this is ridiculous. Oh my gosh. Look at this. Oh my gosh. Now, unfortunately, this is what has to be done. But there is a way to check your answers. Your calculator can do all of that for you. Let me show you. And this only works if you have the newer version of the operating system. So that is why I still need to see all this work, because not all kids have that, and so some kids will be able to do it and some kids won't. So I'm going to have to see the work for everybody. All this work needs to be there for everybody. But for those of you who have the newer operating system, you have the advantage of being able to check your answer. If you go to math here on the left hand side and scroll down, you should see summation. And in summation, it gives you a little sigma thing, and you can put everything in. I can put this whole thing in. So I have n equals 1. Now we're not going to use n's. All we have is x's on the calculator. So we'll use x equals, let me zoom in so you can really see this. Okay. So I have x equals 1, and it goes up to, my n is 5. And then, 5. And then I go in here and all I do is type in that equation. So 4x squared minus 2x plus 7 and equals, voila, 225. So that's kind of cool. Unfortunately, you're going to need to show all your work still, because if every single person had one of these calculators, I think I'd be okay with it, but that's not fair. That some kids can do that and some kids can't. Some kids have to do all this work and some kids can't. So I'm going to require that you still show all the work, but you have the ability to show to check your answer. Okay. Last thing here is explicit and recursive rules. So explicit, we're not going to spend too much time with recursive, though you will see it a couple times, and there's like 1 or 2 questions on your unit test. But we spend most of our time with explicit rules. Explicit rules define a general term of a sequence. So they are defining any term, if you want any term. So for example, I mean, this is what we've seen. Everything we've seen so far has been explicit. So this would be like the a sub n equals 2n plus 3. So if I say I want the third term, you could just, if I say I want the third term, then you would say a sub 3 equals 2 times 3 plus 3. So the third term, or a sub 3, is, let's see, 2 times 3, 6 plus 3 is 9. So if I wanted to find the third term, I would just plug it in. So an explicit rule, this would be an explicit rule that we could use to find any term within a sequence. Whereas recursive rules actually use the previous term to generate the next term. So what that means is if I would have to give you the first term, like let's say the first term is 1, and you would get a formula that says a sub 2 equals, well, it would be a sub n, it'd be any number, a sub n equals 2 a sub n minus 1 plus 3. So this, anytime you see this right here, the a sub n minus 1, this means the previous term. If I have enough room there. So this tells you this is in a recursive rule. It uses the previous term to figure out the next term. So if I want to find the next term, so if I want to find a sub 2, then I would need to plug in the previous term here. So 1 is the previous term, so 2 times 1 is 2 plus 3. So a sub 2 would be 5 using this particular rule. And if I wanted to find the third term, I would just use the second term in here. So 5 would go in there, 2 times 5 is 10 plus 3. The next one would be 13. So explicit rules give you a rule. I want the term, just plug it in. The recursive rules will be using the previous term to actually get the next term. And you'll see some examples here on the last page. I told you, I apologize, I told you this is a little bit long, but hopefully, like I said, you've watched part of this already. So here's some examples of the first 5 terms of a sequence where this is explicit. You see here that you have the a sub n minus 1. That tells us that this is an explicit or a recursive rule here, okay, where it tells you the first term. So this is the first term. First, if I can spell, first term. Okay. Zoom in here a little bit. Okay. So if I want the first 5 terms, okay, I'll just list them right here. Let's see, n, and then a sub n. The first term we already know. The first term is 1. It just told us it's 1. But to get 2 and the rest of these, to get 2, this a sub n minus 1 just uses the previous number. Since the previous number is 1, I just substitute 1 in there, and it's 1 plus 4, which is 5. Now, if I want the third term, I have to use the second term's answer in here. The second term's answer is 5. So 5 plus 4 is 9. To get the fourth term, I'd have to use the third term in here. Third term is 9, so 9 plus 4 is 13. To get the fifth term, I'd have to use the fourth term, 13 in there, plus 4 is 17. And that would be the sequence, the list of sequence, using a recursive rule. I'll make sure, good on time here. So that would be so your answer would be 1, 5, 9, 13, 17. So that would be your recursive rule, or your recursive sequence. So let's try this again. Slide this over. So now this one gives you again the first term. And so we're going to do another list here, n and a sub n. 1, 2, 3, 4, 5. We already given the first term, it's 162. So when you see a sub n here, or n minus 1, that uses the previous term. So what I need to substitute in here is the previous term, which is 162. 162 goes in there, and that's 0.5 times 162. Essentially, you're cutting it in half. That's 81. To get the third term, I use the second term. 81 times 0.5 is 40.5. To get the fourth term, I substitute the third term. 40.5 times 0.5 is 20.25. 20.25 as the previous term times 0.5 is 10.125, and that would be your sequence. And you can write it out if you want. So now the question is, how do you write a recursive rule? So how would we write the rule for a recursive sequence if we're just given the numbers? So when you're just given the numbers, what you would need to find is the common difference between all these. What's being added or subtracted every single time? Well, it looks like it's 10 plus 10 plus 10 plus 10. Okay? In order to write a recursive rule, we need 2 pieces of information. We need a sub 1, we need the first term. Obviously, up here they gave us the first term, so we need the first term, which we have is 3. And then we need what is called d, which is called, that refers to the common difference. D will refer to the common difference, the amount that's being added or subtracted every time. And so that's 10. So what it is how we write this out is just like up here. So a sub 1 is 3, semicolon, and then a sub n just equals the previous number. So a sub n minus 1 represents the previous number plus 10. Okay, because it's adding 10 every single time, it's just the previous number plus 10. So that's this. Remember, this designates previous number here, plus 10. We'll get some more practice with that a little bit later. Again, this is just an introduction, so don't get too hung up on certain things here. Second one. Okay. Again, we need a common difference, or sorry, we need a sub 1 and our common difference. So here we have goes up by, let's see, 24. And that one goes up by, okay, so wait a minute. So here we don't have a common difference, okay? Now, the other way to do this is, well, does it multiply maybe by the same amount every time? I don't know. The way to figure out if something multiplies is just divide the second number by the first number. So if I want to figure out if this divides right, let's do 40 divided by 16. And I get 2.5. Well, then let's check and see if that is truly what it's being multiplied every time. So 16 times 2.5 equals 40. Okay, well that works. Well, times 2.5 again. Let's see if that's the next number. Oh, there you go, 100. I wonder if the next one's 250. Yes, it's 250. And 625. Yes. So we found that actually these numbers are multiplied by 2.5 every time. So there isn't any common difference. So our formula will be a sub 1, which we know is 16, semicolon, a sub n equals whatever the previous number is times 2.5. Or you could write this different. You probably should just write this the other way. 2.5 times a sub n minus 1. Or 5 over 2. I'll leave it as a fraction. That works too. That's writing that. So a lot was there, and it's okay. It's okay. It's a lot of information. Like I said, hopefully you watch a little bit of this already, and so it doesn't make this so long. But that is everything we're going to be doing in this unit. It's just a little blanket sort of introduction to everything we're going to be talking about in this unit: sequences and series and recursive rules. Let me know if you have any questions. Thanks.